early Thursday evening. 3 weeks down. 20% through the semester. You should be thinking about the first exam.
Yeah. Never stops.
We did cylindrical and spherical coordinates last time, right? Yes. Good. We've been studying vectors so far. But what do you notice about all the vectors we've studied?
Three-dimensional.
Sure, only three-dimensional. But the components vary.
I was going to say that's Cartesian. But that's exactly what it is.
Yeah, we can also put that in spherical. They've all been the components constants. That's not really realistic. Vector value functions. So we're kind of progressing along how your math career progressed. Started with just numbers, right? And add, subtract, multiply, divide, all that. Then you looked at, oh, look, variables change. Then it was calculus. We're now in that middle ground. That's what a vector value function is. It's just a vector whose components are functions. So specifically for us, we're looking at real valued functions. Think back to pre-calculus. When you were first introduced to functions, should have been day 1. A function always has what? They're given a function, it has to be paired with something.
A parameter?
Well, it's the independent variable. But it does relate to the independent variable.
An inverse?
Not every function has an inverse. Only one-to-one functions have inverses. Think of how functions define. That's later.
A range?
Yes, they have ranges, but what else does it have? We have to have domains. It's never usually stated, right? It's always an implied domain. What is the domain of a function?
The types of values you can put.
Right? It's the set of all values that the function can take. Deal with that imaginary one. So what do we think the domain of this vector value function is going to be?
Whatever values of t give real outputs for f, g, and h.
It doesn't have to be all real numbers. So values of t that guarantee real values for f, g, and h simultaneously. Now define that using the language of sets. because domains are sets. It's the intersection of the domains. So again, a vector value function, generally speaking, a domain is not going to be explicitly stated, but it always has a domain. It's important to be able to determine that domain.
Look at that diagram using.
That's the intersection. They're not U's either. But that means intersection. That symbol is a cap. It's called a cap. Union would be a cup.
Is it a? Can you say it like?
It's the equivalent of the logical connectivity, yes. Right, and means they both have to be true. To be true, intersection means it has to be in those sets. Or in this case, has to be in all three sets. That's what's common to everything. We said limit earlier. That was you, right? Ask and you shall receive. Who remembers the definition of a limit?
The value of a function as it approaches another value.
That's not the formal definition.
You mean like, so that's minus base over h, or. Right.
Oh no, that's you're thinking of the limit definition of the derivative.
Oh, that's right.
I'm talking about the definition of a limit. It is supposed to be covered in Calc 1. But I find that not a lot of instructors actually cover it. Does the term epsilon delta definition ring a bell? Ooh, that just makes me sad. No good every day, so I'm thinking, That is the definition of a limit. And then there are, of course, definitions for the one-sided limits, limits at infinity, infinite limits, all that fun stuff. But this definition is the only one I really care about right now. So that's a good way to write that down. Now fix this. So now we want the definition for the limit of a vector valued function. Based on the limit of a function, this looks like it's going to be this. Vector valued function R approaches the limit L as t approaches A, written standard limit as t approaches A of R of t equals L, provided that the limit as t approaches A of the magnitude of R of t minus L is equal to 0. And then you use the definition of the limit of a function to understand what that limit means. Right? Because that's just a function, isn't it? A really hideous function, but a function nonetheless. Now that's all well and good for us to understand what a limit really is. But how useful is that to have equals not lined up, right? That's not right. So why is that equals? Looks better. Is that going to be practical for actually finding a limit? You hope not. Just like, would you use that to find the limit of a function? No, right, that'd be kind of a nightmare to do. So we don't really use that definition to calculate limits. It can be shown, and I don't remember if I show it, that to take the limit of a vector valued function, you just take the limit of the individual components. So the limit operator can be pulled into the vector. It's kind of like scalar multiplication. I use that very lightly because it's not scalar multiplication. And this is an operator. Now, of course, this limit's going to exist if and only if each of the individual limits exist. If even one of those limits don't exist, then the entire limit falls apart. So now we're already into Calc 1. We jumped right from pre-calc to Calc 1 with no time in between. After studying limits, I don't want to say after, what did you study with limits? So you studied the limit of a function, and then you used that to formally define a concept you looked at in pre-calc. I hope you didn't study derivatives in pre-calc.
I didn't work with limits in pre-calc, so I don't know.
No, you worked with the notion that we use limits to define in pre-calc. You just loosely defined what it meant.
And did you do?
Well, that's true, but before that.
Slope.
You draw the graph without lifting up your pencil. So you draw your function without lifting a pencil. The function is known as being what? Continuous. You study continuity of a function. So now we study continuity of a vector value function. What was the definition for continuity of a function? So what did it mean for a function to be continuous at a point? So let's say at a point A.
The derivative is defined.
Differentiation implies continuity, not the other way around. Look at the Weierstrass function.
I know what that is.
The Weierstrass function is a function that's continuous everywhere but differentiable nowhere.
It has one value at A. It equals one value at A. If it's continuous at A.
I'll take that. That's one condition. So that's what that means. So it's defined at A. So f of A is defined. That's one condition. I'll give you a hint, there's two others.
Humans exist at that point.
So that's the first condition. The function does have to exist at that point. F of A, so f of A is defined.
I'm thinking sidedness. It approaches f of A from both directions.
Limit exists. So the limit as x approaches A of f of x exists. That's the second condition. There's one more.
F of A equals limit.
The limit has to equal f of A. What do we think the definition of continuity of a vector value function is?
all of the components meet those criteria?
So what does it mean about the vector itself?
It means the vector itself is defined. The limit as x approaches a,
Well, in this case, not x, but yes.
right, it exists, and and it's continuous at a,
Well, you can't use continuous to define continuous. I'll make it easier for you. It's the same bloody definition.
it's the same.
Right, which should be easy to see because each of the three components have to satisfy those three criteria. So f of a, g of a, and h of a all have to exist simultaneously, meaning r of a exists. The limit of each component has to exist, which means the limit of the vector exists. And it evaluates out, each component, the limit has to evaluate out to the value of that component at the point. So the limit of R of t has to be R of a. And then all of the same rules of continuity apply. Vector valued function is continuous over its entire domain. And if you combine continuous vectors, it is also continuous. Right? So add two continuous vectors, it's continuous. Subtract two continuous vectors, it's continuous. Multiply. Well, I guess in this case, take a cross product of continuous vectors. Actually, would that have to be? Yeah, that would have to be continuous. That's not going to change its domain, I don't believe. Scale multiplication obviously still continuous. We do lose something now. We lose composition. You can't take a vector value function of a vector value function. But you could theoretically do vector value function of a single variable function. Right? So your t could be a function itself. Say like a function of x. It's actually a really interesting concept. Is time a function?
Yes.
It is. You can write time as a function of your position. Time is also a function of speed. It's called time dilation. A physics person there will soon learn about that headache. You take special relativity. Find the domain. Express it in interval notation. So remember when you write domains, there's two notations you can use. Interval notation and set notation. we're gonna have to do, we're gonna have to find the domain of each component, right? So let's call that X, Y, and Z for simplicity. Domain for the X, or you could also see it written domain of, right? So you can think of domain as an operator or as a function. And we're going to use interval notation for everything. So what would the domain of natural log of 11t be?
T equals 0 to infinity.
So give it to me in interval notation.
T is greater than or equal to 0.
That's not interval. That's inequality.
Oh, like bracket 0, comma, infinity. Open bracket, yeah.
Domain of the square root of t plus 10.
Open bracket, negative 10 to infinity.
That?
Square root of 0.
So you just contradicted yourself, by the way. You said it's open bracket at negative 10, and then said you can take the square root of 0.
I forget which one is. Oh, wait, the parentheses, you can't take that
For the domain of x, why does 0 have a hard bracket?
That means that you can use that one.
You can't do that with 0, can you? No.
It can, it's just the universe can blow up.
Is that what happens? How do you know the 0?
Same thing if you divide by 0, the universe blows up.
I'm going to do it with my calculator right now.
You gotta be careful.
I believe that used with the old technology, that used to be split mechanically. It would just keep running and running and running and essentially crash your system. We've evolved since then. Just wait till the day that these are quantum. You didn't know that? We have a quantum computer. Wait till we get quantum laptops.
I don't know what a quantum computer is.
It is awesome. You know how fast a computer is? Yeah, multiply that by a magnitude of like 1,000,000. And that's how fast a quantum computer is.
You can fix feedback loops on Zoom.
Probably. Right now, though, they're extremely expensive. Remember how computers first came out? That's how quantum
No, I
computing.
don't remember that. I wasn't around.
That's what quantum is right now. We needed a room about the size of this and it was just a computer.
I wasn't even.
And it was, you need like 80 million fans in the room because it got so hot. And even then it was really slow. But that's the stage where quantum is at right now. It's just you need an entire room for a quantum computer. But soon we're going to have quantum computers in every single room, in every single house. Which means shortly after that, you'll have a quantum phone.
Do you think Apple will change its logo to a cat because of Schrodinger's cat? Instead of
No,
Apple?
my fear is that shortly after the quantum phone comes out, they'll develop true AI. That is the singularity, and that is the doom of the human race.
Ask the AI was not going to reply, watch it explode.
negative infinity 12 with parentheses, and another set of parentheses 12 to infinity. Oh, you can't go to so 0 bracket is 12.
Self brackets negative infinity to 12.
Yep, that's it. So our domain is the intersection of those three. So what do those three intervals all have in common?
0 to 12, parentheses.
That.
Extremely.
You're offered $10 million to change your answer. But if your answer was originally correct, you lose $10 million.
So if my
Would you
answer
take
is
the
right, and I keep my answer, I don't get anything.
So you get $10 million if your answer is wrong and you decide to change it. But if you decide to change it and it's correct, you lose $10 million.
Yeah, so I'll just keep my answer.
But you're not out that many times.
Am I allowed to change my answer to what I had it
Nope. That's not change.
Okay.
And again, it's another weird physics concept that we used. Say you start at point A and you wind up back at point A. But you walked in a circle. Did you change your position? No.
That's like overall velocity is 0, right? Yeah.
If you go to bed in the same bed you woke up in, your average velocity for the day was 0.
Depends on if you go to bed in the exact same position.
Now, I could argue against both of you that you actually still have velocity.
Well, if you consider like your bed and inertial reference frame, you don't worry about the motion of the Earth or whatever. So
Even if you ignore the motion of the Earth,
motion of the solar system, or
the sun's still moving. The sun moves around the center of our galaxy, but our galaxy is moving. So is the universe, actually.
well, none of that matters if you consider your house a reference frame.
We don't like open reference frames in physics. Yeah, physics sucks. You have to consider everything. Let's see who remembers. Vector parameterization. With the idea of vector valued functions comes the idea of parameterizations. what was it, last week we looked at lines, and then set of parametric equations for lines. Yeah, we're not gonna do that anymore. Now it's gonna be a parameterization of the line. And you briefly touched on this concept at the end of Calc 2. Right, you had a set of parametric equations, x and y, but then you also said, oh, but you could also write that as C of t. Yeah, that's just a 2 vector. Which is why it's stupid that it's covered. And then I have to recover it. We just now extend that to space. So we're going to be looking at the parameterizations of curves. So plane curves and space curves. And eventually we'll move on to parameterizing surfaces. So parameterization of a circle of radius 6 in the xy plane centered at the origin. What would the x component be? Six, just 6?
6 pi.
I agree with the 6.
6 cosine theta.
What about the y?
Sine theta.
Not done yet.
Z equals 0.
Still not technically done.
Theta is all real numbers.
Here for 2 pi.
Or 2 pi to 4 pi, right? Or 4 pi to 6 pi, or minus pi to pi. Or pi to 3 pi. Some interval of length 2 pi. There's our parameterization of the circle. Verify that's a proper parameterization. C being 0 guarantees we're in the XY plane, so that's fine.
How do you read the upside down, dot triangle there? Oh, thank you.
It's that since, because, and something along those lines. How are we going to verify? Hmm? Well, that is definitely proper domain. But how do you know this parameterization works? What would the equation of the circle be? What's the relation?
36 equals x squared plus y squared.
What was x? What was y? That better equal 36. X squared plus y squared equals 36. Is this the only parameterization?
No, if you open it up to different coordinate systems, right?
Ignore the coordinate system.
Okay.
I guess you would really be ignoring coordinate systems.
Is it?
I can think of at least two more. One is obvious. Would that also work? Let's go to whether it does. One that's less obvious. That actually would work. That would give me a semicircle. Oh. Still don't want those holding a semicircle. Those are right. Point is, there's theoretically an infinite number of parameterizations. That's the most common one for a circle. You may want to remember that. is, right? Enough room to actually bring it on each part. So vector parameterization for the line through the points 4, 1, 1 and 9, -3, 3. Satisfying first the condition that R of 0 is the vector 4, 1, 1 and R of 8 is the vector 9, -3, +3. What was the set of parametric equations? So x equals what?
X equals x0 plus at, y equals y0 plus bt, z equals z0 plus ct.
So just write the set in vector form, and it's not difficult to see this. For what t?
T hard rockets 0 to 8.
Why just 0 to 8?
Because those were the two values that we were required to do.
So think more in general.
All real numbers?
By the way, just because a line only contains, we're only given 2 points of a line, does that mean those are the endpoints of the line? So it'd still be minus infinity to infinity. Now, if it was only a segment, then yes, I'd agree. Like your t would be restricted. So first, the direction vector. And this direction vector is going to be the same for all the parts. How are we going to find the direction vector?
Find the vector PQ.
Which is what?
5, -4, 2.
Theoretically, does that have to be T? It's not just T, that's if I say that is a function T of U, can I still get every real number? Can- If I just let U go from minus infinity to infinity, I can still get every real number for T. So as long as we're multiplying by a function that gives you every real number, it doesn't just have to be T to the first power. And remember, that's just a dummy variable. We're going to use that to our advantage. Pick a point, P or Q. Now use the given condition of R of 0. First, plug in R of 0 to what we just wrote down. What do you get? Plus something.
Zero.
What is it?
F of zero.
F of 0 what?
F of zero times 5 negative 4 2 vector.
We want that to be 4, 1, 1. Looking at that, what does F of 0 have to be? F of 0 would have to be 0. The E
T equals T.
more general.
F of T equals 0.
No, I mean, that's definitely true, but that's not going to be helpful. More general than just T.
1?
That's less general. Some number times T. Like, remember, we still have a second condition we have to find. R of 8. That has to be what? Nine, negative 3, and 3. So what's on the bottom? Subtract from both sides the vector 4, 1, 1. Eight n times 5 negative 4 2 has to equal what?
Negative
n have to be equal? Which means n has to be what? There's your parameterization that satisfies the condition. R of 6 now has to be P, R of 10 has to be Q.
Professor. So we can say that when we see vector, or so we can basically go from calling P a point to a vector like that? Okay.
Because it's just going to be a directed line segment rotate.
Oh, okay.
So really just converting into a vector.
Okay.
And that has to equal 1, 1. What's f of 6? F of 6 has to be 0. Let's make f of t n times t minus x. Once again, where n is just some real number. So R of 10 Yeah, I'm not there yet. I'm just plugging in 10 to our original parameterization and saying that has to equal Q. What are we going to multiply by?
N times 4.
And that has to equal that. You subtract 411, what do you get? What does 4n have to be?
One.
There would be a parameterization.
And that 5, -4, 2, that's the direction, that's PQ, right?
That is the direction vector.
The direction vector.
Right, so that is from what I wrote
Yes.
right there.
Yeah. Cool. Thank you.
And so P and Q correspond to the values t equals 0 and t equals -2 respectively. And so look at R0 first. So R of 0 has to equal what? Which is
4, 1, 4, 1, 1.
so once again, f of 0 would have to be 0, right? So let's just take f of t to the n times t. R of -2. Has to equal I'm sorry, that's not n times t, is it? -2n. So what would n have to be? So there's a parameterization. And that's all the same line, by the way. Parameterization of x equals negative 5z squared in the xz plane. So what are we thinking?
Is going to be 0.
Sure.
Oh, no, no, I'm not, never mind. Because y is anything, right?
Negative 5z power q, comma, 0, comma, square root of x over negative 5.
What's your parameter?
So all real numbers.
You have two variables in there.
Should be t.
That wouldn't work. So which of those two is your parameter?
Just c.
So what I would now need to do is switch that from R to T to R to Z. For what? So what's the domain?
All real numbers for z. For z is all real numbers.
Yeah, that works, and that's the easiest one to do. Shame you weren't sure about why we do it.
I lost my nerve.
The idea of parameterizations, very, very important. In fact, every curve that we study will be a parameterized curve. So we'll always represent a curve as a parameterization. I need to find how do we evaluate limit of a vector?
Limit of each term.
What is that first component? How'd you get it?
Anything to the zero power is 1, 2 times 1 is 2.
Where's there a zero power?
Because you substitute 0 for 2.
Why?
Because that's what the limit is to.
But why? It is, but why? Why are you allowed to do that?
Define that.
Okay,
It exists.
so what does that mean?
Well, it means that that's the limit at t equals 0. Why? Because that's.
What theorem are you using?
I don't know.
Again, this should have been covered in top one.
It was.
So the composite function theorem. Which states if you take the limit as t approaches a of f of g of t, the limit of g of t is L and f is continuous at L, then that limit is f of L. So what is the limit as t approaches 0, 0? That was name. Limit as t approaches 0 of t, I'm sorry.
So it's 0?
Is e continuous at 0? So is e to the t continuous at 0?
No.
That's not.
Well, I mean, yes.
So then your limit e to the 0, which is 1.
Right.
Right, so direct substitution only works if it's continuous. What about that second component? You can.
Well, because if you just put 0 in for t, you get the indeterminate form of
Right.
0 over 0,
That's true.
which you can kind of get around by just doing changing it with L'Hopital's rule
That's true.
to negative to the derivative of sine negative t over form.
Which is what?
It's negative cosine of negative t.
That's true.
So then that'll give you negative 1.
That's true. That's the correct limit. would you want to do that? You know that limit.
It's just one of those givens we should remember. Okay.
It's a special limit from Cap 1. Just multiply the denominator by -1, multiply the result by -1. Sine of negative t over negative t, that limit is 1. So you know it's -1. A lot easier than what we have. Yeah, you're not incorrect. You just did more work than you did before.
And I would like to avoid that. So,
What about that final component? There's your limit.
like a dance class or something.
Again, really boring limits. Boo to you. I'll have to open up a textbook.
Sounds like they're playing jump rope over there.
Now we're back.
Well,
Clearly not.
So,
No, it's not.
Should we open time to stop having origin? That's almost as bad as them letting the kids out in daycare during finals.
Oh, yeah. Yeah.
Like, I understand it's a daycare, but maybe not let them out during finals week. Just saying. Freaking dance class or something?
it might be.
That is that room, right? 2101. I'm gonna look up to see what class is down there. So what is that first limit? What is that second limit?
2/3.
No.
Pi over two.
Pi over two. Right. What you would do with that one is you do a change of variable. Let u be 2t. As t approaches infinity, what does u do?
Approach infinity.
So those are the same limit. Just makes it easier to see. So then the idea becomes, what is the range of the inverse tangent?
Negative pi over 2 to pi over 2.
So you have to keep that in mind. It's minus pi over 2 to pi over 2. Where are the vertical asymptotes of tangent?
Pi over 2 and negative pi over 2.
Of those two, when you take the limit of which one, or you take the limit as x approaches, which one of tangent of x gives you infinity? Pi over 2. Specifically, it's going to be from the right, or from the left. Right, but if you look at the graph of tangent, just from minus pi over 2 to pi over 2, goes down negative infinity at negative pi over 2, up to positive infinity at pi over 2. So the limit of the inverse tangent of u as u approaches infinity is pi over 2. Group council and education setting. Okay. What's that for us? Oh, wait, no, sorry, that's what I said. That's even worse. Sociological research methods. Tuesday, Thursday, 5 to 6:15, so that can't be it. That is what? 15:30 to 16:45. No, that's not it. There's no class over there, which means it is a review. Which means they should be more respectful. Do that again, I will. What is that first limit? What is that second line?
One over two.
How'd you get it?
Comparing the exponents of the numerator and denominator.
That
That's not right.
only
Sorry,
works if it's going to infinity.
wrong unit.
Because I agree, it is one. It could be like thousands and zero. Plug in 4, what do you get? Isn't t minus 4 difference of squares? Which would give you 1 over root t plus 2 ever, except that t equals 4. Which means those two limits are the same. Now plug in 4, you get 1 over 2 plus 2. Ah, which means it should be 1/4. And what is that third limit?
1.
So there's your limit. Questions on vector value?
Yeah.
Pretty straightforward, right?
A good review of things.
What did you do after limits?
Oh goodness.
In calculus, or went right to derivative?
Yeah.
And then what came after derivative?
Integrals?
So guess what we do next?
Both?
We do derivatives and integrals.
All in vectors.
Have a good weekend.
You too.